There we go. Okay, welcome back. Yeah, the idea for this entire week, at least, is going to be, so this is lecture 17. And the idea for this week is going to be connectedness. So there's a chapter on anchors that's about connectedness and compactness. It's like two properties you can or cannot have if you're a topological space. So what's kind of the idea here? It's something like, I don't want to give too crazy of a description, but if your space looks like this, you have like these two pieces, right? And that means you somehow can separate your space. And the idea is maybe it looks like that, but then what I mean is maybe these guys are not like open sets. But if there is a space here, you can separate them into two open sets that will cover everything. And if you happen to have even more pieces, that still will be okay. You can always like put one to one side and the other to the other. And these guys, they can be really close without intersecting. Yep.
Cover everything. Just like the covering, the same idea as the covering.
Like the union will give you the entire space. So this is kind of the picture. Something like this shouldn't be connected because it's not connected. And now we need to like formalize this thing, and I'm just going to write the definition because I think that drawing is the best we can do. So definition one, main definition for this week. Let's start with topological space. Topological space. I'm going to define two things. The first one is, what's a separation of X? I'm not really going to use this that much, but since the textbook uses it, let's use it. So separation of X is going to be a pair of open sets U, comma V. So you should think about these two guys over here. Maybe I can start using some colors. So this would be maybe your U. Maybe let's use some colors here. So U and B, maybe this is my U. Open. Don't have any shape, of course. B. Doing something like that. And the important thing is these need to have three properties. The first one is they are both not empty. They cover the entire space. And they do not intersect, so they cover efficiently. So this is the picture you should have in mind. And let me say something here. Forget about this. These two conditions are obvious. I mean, not obvious. These two conditions are something you can always like cook up. If you are in any topological space, you can take, for example, U to be X, which is open, V to be empty, which is open. They will, of course, satisfy this, and they will intersect trivially. So that's not the crazy part of the definition. This is the crazy part. This you can always do. This is the crazy part. And the second part is we're going to say that X is connected. Any guesses? When is X connected? Right, when you cannot do such thing. If there there is no separation.
That because the implications that sets have to be connected because you can't have these separate sets.
What's the question?
Like what you just defined is essentially you can have these separate open sets U and V such that they don't intersect, they're not empty, and yet their union covers the entire set. So if that isn't the case, then like the reason it's called connectedness is because any two sets U and V have to intersect. Is that kind of like their intersection can't be empty then?
Yeah, that's one way of yeah. We will go through several characterizations of that. Yeah. So yeah, maybe let's go there now. But are we okay with this? So the kind of thing here, it's clear when you can disconnect something. Maybe let's use more space here. So it's clear. In some cases, it's clear that you can separate. Like the picture is clear, and you define connectedness. Well, when you cannot do that. And of course, I will use sometimes disconnected when this happens, if there is a separation. So let's go with the first lemma for today. Lemma 1, let's call this. So let's take a topological space. Topological space. So this is the definition. And this is my lemma. The following are equivalent. The first one is going to be X is connected. The second one is going to be sort of this thing. So I want to emphasize that the important part is U and V are not empty. For every open sets U comma V with X given by the union and trivial intersection, either U is trivial, maybe empty, or V is empty. I could also say U is X or V is X, because one is the complement of the other. So what I'm trying to emphasize, this is the kind of usually the crucial part. And this is how you prove something is connected. You say, well, let's take U and V open sets such that this, let us show that one of them needs to be empty. Yeah.
The standard topology as an example with like an open ball, because any U open, right, you have this like dotted boundary. You can't have it's like impossible to have these two open sets connect and cover the entire set because you'll always have this like dotted boundary. So the only way that can be the case is if they don't have like
Okay, part 3 is maybe this may come as a surprise, but only for a second. The only subsets of X, that are both open and closed this is also called, probably one of my favorite words, clopen.
This when it's going through the book, can I say for any topological space, the empty set and X are always clopen?
Yeah, absolutely. So what I'm saying here is those that you always have are the unique that you can have. So the only subset that are both open and closed are the entire space and the empty space. So the proof, let me maybe say something very briefly. I'm not going to give you a proof. I'm just going to give you an idea. 1 and 2, there is just a logical formality. So what if and only if two, there is no math here. Let me just say it's just a formal statement. It's just logic.
It's two is defined as like the definition of one, right?
Well, not really.
Or it's immediate from the definition.
Yeah, it's just logic. Yeah. Is it clear? And then maybe two if and only if three. The idea here is this follows from this very easy fact, or maybe this easy observation. X equals U union B, and U intersects B equals empty, with both open. This just gives that V, they give you the entire space and they are disjoint. So this just means that V needs to be X minus U. Right? These two things just means V needs to be X minus U, but you want V to be open. So you want this guy to be open. So U is closed. So to be completely honest, when you take two subsets, two open subsets that will give you the union, such that their union will give you X, but are disjoint, you're just taking a subset and its complement. If you fix U, V is fixed. So it's like no, you never have two sets satisfying that. You just have U and its complement. Are we okay with this? Yeah, great. So examples. Maybe it's time for us to do some examples. Maybe first example is if you take a set and you equip it with the trivial topology. So remember here, we only have two open sets, the empty set and X. Then also you have exactly two closed sets. So you have exactly two clopen sets, those two. Yep.
Because the empty set and the full set X are both clopen, couldn't you then make an argument that if they're in that trivial topology, if they're both connected and separated?
What? Who is connected and separated?
It's like if your U and V is X and empty, then don't those sets satisfy both conditions to be separated and connected at the same time?
I don't know what's a separated set.
But I'm saying a separation of X is a pair, right?
Yeah, it's very important that U and V are not empty. That's the crucial part.
Okay. So you can't do it with a trivial topology because you can't be S squared. Okay, got it.
Yeah, you don't have two empty sets to start with, the two non-empty sets to start with. So second one is almost every discrete space. So remember here, everything is open. So of course you can partition things, but you need to have at least one element, because if you're just a point, then you're going to be connected. So every discrete space with more than one element is going to be not connected. So why is that? In fact, let's call this space X. In fact, if you have some point x in x and something else, then this thing here, x given by the singleton union its complement, is a separation. And this guy is not empty because you have more than one element. Because the cardinality of the set x is bigger than 1. And of course, they are both open because everything is open. So okay, maybe more interesting example 3. Let's denote this by y. It's going to be so here I'm starting to I want to show you something kind of tricky. So going back to our picture up there, the fact that you have two open sets separating parts doesn't mean that the parts are really at some distance from each other. So there it's quite clear that there is like some distance between parts. But for example, here, this is a subspace of the real line. What do you think about this space? So it's something like this. It's something like this, -1, 0. Maybe that's not what I want to do. I want to do something like this. So this is the real line. This is -1. This is 0. This is 0. This is 1. And there's no space here. So what do you think? Is this guy connected? It's not, because we are defining it with a separation. So is not connected. Not connected. Because these two guys, -1, 0, is open in Y. And also the other guy, 0, 1, also. So we're giving it by a separation. These two guys are opening Y because this is, for example, -2 open intersection Y. Is that clear that these two guys are open? Sometimes confusing that you have the closed point here, but for example, this is -2 open 0 intersection Y. So it's open in the real line intersection Y. So we're not saying that you need to have like space between your parts. That's not what's going on. Okay. Any questions about those examples? Yeah.
In the general, like, you explain again why -1, 0 is open, why, even though it has the closed.
Because of this. It's an open set in the real line, in the big space, ambient space, intersection with your subset. And that's how you define open sets in the induced topology. Okay. So let's investigate this sort of thing for a second now. I will take inside an ambient space, I will try to study different subspaces and see where I can be sure that some stuff is going to be connected or not. So I will switch to blue because yeah, black's not working. lemma, this is probably lemma, yeah, 2. So let's take a topological space. And let's take a subspace. So what I mean by this is a subset with induced topology. Maybe I don't want to use A, sorry, let's use Y. So when is Y going to be connected? I'm going to use like the part 2 over here of our 3 equivalences. Then Y is connected if and only if for every, so in principle I should talk about open sets in Y, but I will talk about open sets in X. So this is the crucial part here. I don't want to use open sets in Y because they depend on open sets on X. So this is what this lemma is doing. If and only for every open sets U and V in X, such that I don't want to say that Y is the union, but I want to say that Y is included in them. And I don't want to say that these two guys intersect trivially. I want to say that they intersect trivially when you intersect them with Y. So in this case, if you have such thing, then either Y is a subset of U or Y is a subset of V. So what we're doing here is something like, so suppose the ambient space is like the 3-dimensional space, and we have this to be our Y. So I don't want U union V to give me Y. They could be bigger. Maybe this is your U, because it's an open in the space. Maybe this is your V, could be bigger, right? But what I want is, I want them to intersect in Y trivially. So this is not really what I need. Something like this is okay. They can intersect outside of Y, but I don't want them to intersect in Y. So the proof for this will be homework assignment. And the crucial part here is, if you let U prime to be Y intersection U, V prime to be Y intersection V, these are open in Y. Which have this union and intersect trivially. So that's the idea. And what we're doing is exactly trying to get rid of this kind of weird behavior when open sets in Y are just open sets in X with some intersection. And then instead of having an equality here, that will just translate into an inclusion. And instead of having an trivial intersection, you need to intersect them trivially in Y, like this sort of thing. Are we okay? So that's a helpful lemma to be sure you understand the definition. That's going to be not in this homework assignment, on the next one, because this one is about quotient spaces and sequences, I think. Yeah. By the way, it's already available. So yeah, maybe before I go down, let's say, so what about these examples here? We're either proving stuff is not connected, or it is connected when it's coming with a disconnection, with the separation. So in principle, because of the definition, let's look at part 2 here. In principle, it's going to be harder to prove that something is connected than showing it is not. Because it's like showing is you need to give me a separation. You kind of need to give me an example. But proving it's connected, you need to prove that that's never possible unless the sets are empty. So it's kind of example versus proof thing. So maybe, I don't know, this is a very informal note. Proving, of course, this is nonsense because there is no real way to compare these things unless you do like some complexity theory. But proving connectedness is in principle more challenging or harder than, and instead of proving, I will say exhibiting a separation. Coming up with a proof is more complicated than giving an example. That's kind of what I'm saying. And you know that's not always true. But I want to point it out because what I will do now is try to assume I have something connected and see if I can cook up more connected stuff. That's essentially what's coming next. So proposition 3. So this one is, I think, very instructive. So assume we have a family. Let me call this A i's, where I lives in some index set. But I'm not going to do the product of them. I'm going to do something easier. Assume we have a family of connected subspaces of a connected space of a space X. Now let's look at the picture. Of course, the union of connected things need not be connected, but if you are sure that there is something in the intersection, then the union AIs is a connected subspace of X. So the picture is something like, I will just use one color for all of them. Or maybe I can use more than one. So you have one connected subspace, another one, and a third one. And you can be sure there is something in the intersection. Then you can prove the union is going to be connected. So is the picture kind of clear? Because this should be very, I mean, from an intuition point of view, this theorem should be true. Otherwise, we're in trouble. But this should be true. So let's give our maybe first proof for today. So of course, this point is going to be very important. So let's just take that point to begin with. So fix some point Maybe I don't want to use X. I'm using X on my notes, but probably X is not a good idea. Maybe let's go with Y. Do I have a Y? Oh, no, but I want to call this guy Y. Z. Let's take some points in the intersection, which we know exist because the intersection is non-empty. And let's call this guy Y. Let Y denote the union of these guys. Of course, with the induced topology. So we want to show these guys is connected. We want to show Y connected with the induced topology. So I'm going to use my lemma. Instead of taking open sets in Y, I'm going to take open sets in X. So using lemma 2, or maybe instead of using with lemma 2 in mind, take open sets U comma V of X such that the set Y is inside the union. And when you take the intersection of them with Y, you get the empty set. And what we want to show now, so what we want to show using lemma 2, either Y is inside of U, completely inside of U, or Y is inside of V. And something that I'm not saying here is if in first case, if Y is inside of U, then the intersection of Y with V is empty. So Y is completely inside of U without intersecting V, because the intersection of the three guys is empty. What I'm trying to say is in lemma 2, when you say either Y is inside of U or Y is inside of V, I could also say, because these are just the same, either Y is inside of U and intersects V trivially, or Y is inside of V and intersects U trivially. I could just add those and that will be the same, because I'm asking them three to intersect trivially. Okay. Is it clear? This is what I want to show. Maybe think about what I just said while I erase this. And what I'm trying to say is those statements are stronger than they seem. Not only Y needs to be inside one of them, it also needs to intersect the other one trivially. And that's just going to be a consequence. Okay, what can I use? What can I say now? How should I go on with my proof? That's the setup. What can I do? Well, I should use this at some point, right?
Maybe by contradiction, having sets in, like in part of the family of connected subspaces, and then showing that they.
That would be a good idea. But yeah, that's actually a very good idea. Well, probably let me say it's a messy idea, but it's a good observation, because usually that's what you'll try to do. You'll take like open sets in each AI and try to do something. And that's exactly why I'm trying to point this lemma 2 thing here. Because you can get rid of subsets of your space and go to open sets in the big ambient space. So if this happens for Y, it will happen for each AI. Because AI is inside of here, and the intersection of these two guys with AI is even smaller than this. Right? So at some point I should use that, but let me leave a suspicious space here. So since AI is connected and AI is a subset of Y, this is not the important part, this is the important part. AI is inside the union with AI intersect U intersect V, subset of Y intersect U intersect V, which is empty. By our lemma 2, either AI lives on the first guy or on the second. Okay, so this is an argument we should use, but what's the problem with this? What's the problem with this argument? Well, it depends on I. So at some point, I want to show Y is inside U or inside V. But maybe A1 would be inside of U and A2 will be inside of V. That will be problematic. Because then Y will like have pieces in U and pieces in V. So we need to show that's not possible. What's the anchor that we're missing here? That's our point. I don't know the name. This point. So let's write that. This is the crucial part. Since our point lives in Y because lives in the intersection which is smaller than the union, which is inside of U union V, we have either C in U or C in V. But not both, because otherwise Y intersect U intersect V will be non-empty. This is not very important. At this point, it's not very important. Then it will be very important, but right now it's not. Yeah. Mm-hmm.
Are U and V necessarily disjoint?
No, that's the picture here. U and V can intersect outside of Y. That's what I'm trying to like picture with this kind of guy. They could intersect outside of Y, but I don't want them to intersect in Y. That's what this means. So that's exactly what we're saying when we say Y intersects U intersects V. Sorry, it's empty. Okay, so one of these two guys. So let's assume it's U. Assume, of course, that without losing generality, that C lives in U. And now I will fix an arbitrary index I. Fix an arbitrary index I. So I have one of these two things. And I want to discard this one. I want to get rid of that option. Right. If you happen to have this, in case AI is a subset of V, we'll get, we have Z in AI, which is inside of V, right? So C lives in Y, in U, and in V. C is a point in the intersection Y with U with V, which is empty. So this case is not possible. AI can never be inside of V. So that means we need to have AI inside of U. And that's for any I. So this is for any I. Maybe I can say, what's this? Thus, AI is inside of U for every I, which means that the union, which is called Y, is also inside of U. And that's what we want. So that's how we will finish our proof. Any questions? So I think this is a very instructive proof. Maybe try to replicate this on your own. I really wanted to leave this as an exercise, but at some point I needed to prove something. I think it's very, very instructive proof. Okay. So the next proposition, by the way, some of these things could be called theorems. Probably this one, proposition 3, shouldn't be a theorem. This one maybe could, but I feel it's not that heavy. So assume now still leading with subspaces. So assume A is a connected subspace of some space X. Then the claim here is that every subspace P of X, and by that I mean any subset with the induced topology with this property A is contained in B, which is contained in the closure, is also going to be connected. So before we maybe let's try to do a picture, which is not really that helpful, but our A could look something like this. You have some interior points, some closure points, and then this will be the closure. So this will be a closure. This will be A. Of course, closure contains everything inside of A. And then your B can be like any intermediate thing. So your B could maybe be something like solid here and then open. That could be your B. Yep.
I don't understand how we can define sets with interior points as partially open and partially closed without them being like open. But how can we define? How can we have A where part of the boundary is closed and the other part is open? Because isn't that how you define A? Part of it is dotted and part of it is.
Yeah. Well, first thing is we never defined what's the boundary of something. But an example of this is something like this. Or maybe if you're in like R2, it's like you take the open ball and you take things here. Like this half, you want the distance to be at most one. Oh, sorry, at most one, and here strictly smaller than one. But yeah, it's easy to define those things. So this is kind of the situation. Right, and usually it's very hard to draw closed sets. The thing is, yeah, they are usually, unless you have like different pieces on different like connected pieces on a set, it's hard to draw. Okay, so what are we actually saying here? So this is from the practice midterm, which, by the way, could be a theorem in the class. The closure of A is A appending some stuff. And the stuff is what's called cluster points. So these are things that for every neighborhood of the point, maybe you subtract the point and you will still intersect A. So what we're saying here is if you append cluster points to A, which is connected, then you will still be connected. So the theorem says, so prop says, if you adding cluster points will keep subspaces connected. What I'm trying to say, this is probably very, very poorly written, is you will not lose connectedness if you add cluster points. So what I'm trying to say, that's the only thing that V could be. It's A union some cluster points. It's also called limit points in bankers. And as you know from the midterm, in a first countable space, limit points for a subset are limits of some sequence. But in a space that's not first countable, that might not be the case. Do you follow what I'm saying? Talking about the midterm here. Okay, proof. Here we're just using our lemma 2 as hard as we can. So the proof is, again, using lemma 2, or I should say again, with lemma 2 in hand. We want to show V is connected. So let's take U and V open in X, which cover V. So V is inside the union. And U and V maybe don't intersect trivially, but they do when you also intersect them with V. So at some point, want to show, at some point, either V is inside of U or V is inside of V. And again, kind of the only thing we can use is that A is connected. So since A is connected, and we have the following, A is inside. So here I'm pretty much replicating what I did with my AIs. So A is a subset of V, so it's a subset of the union. and the intersection gets smaller, right? In this case, we have either A inside of U or A inside of V by our lemma. Okay, so what should I do now? We kind of have two cases for A. Want to show something like this and know something like this. So the obvious step here is assume this is the case, A inside of U, and prove V inside of U. So let's assume, again, without losing generality, because the other case will be exactly the same, that A is inside of U. And now let's prove V is inside of U. So let us show V is inside of U. What can I do? How do we show V is inside of U? Well, kind of element chasing. So take an arbitrary point X in B. And now to show that X is in our set U, since V is inside of the union, it's enough to show that X cannot be in V. It is enough to prove that X cannot be in V, right? Lives in the union, not in V, needs to live on the other one. So here we go for a contradiction. Assume X is in V. I'm trying to use my closure properties. So in this case, then X is not an element of the complement of V, which is closed. And I'm doing that because I have to use that V is a subset of A closure, right? So X is not an element here, which is closed in X, of course. Now, not only that, this X minus V since A is inside of U, X minus V contains A. And this is because A is inside of U, and intersects trivially V, right? So when you do A intersects U intersects V, this is just A. This is just A. So this is A intersects V, and we're assuming this is empty. Well, we know it's empty. Yeah, sorry, it's empty. Thank you. Right? So A and B intersect trivially. That means A is inside the complement. There's nothing in common. Now, do you see the problem with this? Do you see the problem with this? There's a problem. Right, but I need to use at some point that B is inside the closure of A. At some point, I need to use that. But what's going on here? Hence, when you take the closure of A, which is by definition all closed sets in X, which contain A, so X minus B is one of these guys. X minus B is one of these guys. That's what we just said. Right? That's a closure. But this guy, we're assuming contains B. But we're assuming X lives in B. But this is a contradiction. Maybe let's say, but X lives in B, which is inside the closure, which is the intersection of all closed sets. Hence, X needs to live in X minus B. And that's a contradiction. Yeah, maybe. Yeah, I'm not really proving this by contradiction. This was a mistake.
Yeah.
Because this, here I'm saying X lives here, and also that's not. And that's the problem. Not the thing that's wrong, but I don't really need a contradiction. Okay. So this proves that X lives in U. So maybe let's say contradiction. Therefore, X lives in U, and that's for any X. So B is a subset of U, and that's what we decided. Yeah, let me hit stop because we're on time.